Have you ever wondered about the very interesting analogy behind sunsets on Mars? Well, if you haven't, you should, because the sunsets there are blue in color. That's right. Everyone may agree that a sunset is one of nature's wonders that speaks to their introspective side. The reds, oranges, and pinks that envelop the sky at twilight inspire artists of all stripes to become introspective and create works of beauty. Meanwhile, Mars sunsets lack the Earth's crimson majesty, since the reddish hues are not present on the red planet. Let's take a look at why that is so. There's something remarkable about the connection between Earth's and Mars skies. The sky above our bluish-white planet is mostly blue, but it turns orange at sunrise and sunset. By coincidence, the orange-brown sky of the red planet throughout the day gradually changes to a bluish palette as the sun sets. So, if they're both being illuminated by the same star, what gives? The sun appears bluish-white from the surface of Mars, according to data gathered by many rovers. In addition, the sun at sunset appears to be encircled by a blue light that gradually disappears, blending in with the reddish-gray Martian sky. But why does this happen? Well, the answer is in Mars' peculiar atmosphere. There are then 7 distinct wavelengths that make up the visible spectrum, which we collectively refer to as white light. These wavelengths are commonly referred to by the well-known term Roy-G Biv. In essence, various planets get the same source of electromagnetic radiation but at varying strengths. Yet what about the fact that every planet has a different shade of sky and sun? This is due to the fact that the medium through which the sunlight travels also has a role in determining the colors we perceive. In addition, Mars has an atmosphere that is roughly 80 times thinner than Earth's. However, dust particles predominate the Martian atmosphere. Mars' blue sunsets are further largely attributable to the dust particles of zeolite, hematite, olivine, and magnetite that coat the planet's surface. That said, light scattering, as we've established, is proportional to particle size. On Earth, where atmospheric particles are smaller, Rayleigh scattering is more common, but on Mars it is less so. Its atmosphere contains dust particles of diameters between 400 and 700 nanometers, which is almost equal to the wavelength of visible light, and hence is too large for Rayleigh scattering to occur. However, they are governed by a separate optical phenomenon known as Mie scattering. It is commonly believed that Mie scattering distributes light of all wavelengths uniformly. However, the wavelength that they mostly scatter changes depending on the size of the particles present and the direction of the incident rays. This means the redder the light is, the more it is scattered by the dust particles in Mars' atmosphere. And because of this, and because Mars has so much red iron oxide, its skies appear red and its sunsets appear blue. But if the sunset is so hot, why does its disk look blue on Mars? The Martian atmosphere absorbs the redder wavelengths, making the sun appear blue from the red planet. The dust particles on Mars are the ideal size for scattering red light, thus they do so at the expense of blue light. So, at sunrise and sunset, when the sun has traveled the farthest, the redder wavelengths of light have died out, leaving only the shorter, bluer ones. This phenomenon, known as wavelength selection extinction, is thus responsible for the sun's bluish hue. On that note, I'll end this video here. I hope you enjoyed it. If you did, please give it a thumbs up and do not forget to subscribe to the channel. Thanks for watching, and I'll see you at the next one.